Hello, fifth period. Welcome in. Hopefully you've had a chance to work the warm-up. Mine says week 1, class 1, but yours says week 1, class 2. It's the same document. We're going to go through these answers first, then we're going to talk about the notes for today. So let's dive right in. Here's number 1. You should have worked this already, and you should have partnered up and talked about this with your partner. Hopefully you got the right answer. Let's take a look. Maria has a collection of marbles. She has 12 red marbles, so red is equal to 12, and 30 blue marbles. Blue is equal to 30. Find the ratio of red to blue. Whatever comes before the word to is going to be in the numerator. That is red, red to blue. Whatever comes after the word to is going to be in the denominator. That's the word blue. So 12 red to 30 blue. We can divide both of these by 6, and we get 2 to 5. That's the ratio of red marbles to blue marbles. If you want to write a sentence for this, the simplified ratio of red to blue marbles for Maria's collection is 2 red to 5 blue. Next one, what's the ratio of red marbles to the total marbles? Well, we've got 12 red, we got 30 blue, so 12 red, 30 plus 12 is 42 total. The red marbles, 12, to the total marbles, 42. We can divide both these by 2, 6 to 21. We can divide both of these by 3. We get 2 to 7. So the ratio of red marbles to the total marbles is 2 to 7. Next one, what's the ratio of blue marbles to the total marbles? Well, again, we have 42 total marbles. That was 30 plus 12. We have 30 blue marbles. Blue marbles to the total marbles, that is 30 to 42. We can divide both of these by 6, and when we do, we get 5 to 7. So that is 5 blue marbles to 7 total marbles. That is the ratio of the blue marbles to the total marbles. What is the ratio of blue marbles to red marbles? Well, on the first problem here, we found the ratio of red to blue was 2 to 5. So the ratio of blue to red is going to be 5 to 2. 5 to 2 there. Number 2, in a bag of candies, the ratio of chocolates to gummies is 320 to 460. How many total candies are in the bag? 320 plus 460, you add that up and you get 780. Now, this is not a great question, and here's why. We were told that the ratio of chocolates to gummies is 320 to 460. That doesn't mean there's exactly 320 chocolates and 460 gummies. We weren't told that explicitly. We assumed that that's the case, but we weren't told that explicitly. On a test or a quiz, I will word this in a way that is better, where there is less room for interpretation. So anyway, if this were a test or a quiz question and you missed it, and let's say you told me the answer was 32 let's say you told me that, I don't know, the answer was 78, right? Maybe you assumed that there were 32 chocolates and 46 gummies, and you told me there were 78 total. I would have to seriously consider taking that because this is not worded well, but you get the idea. Let's keep going with this problem. What is the simplified ratio of gummies to chocolates? 460 gummies to chocolates, 320. You got to be careful here. Whatever comes before the word to is going to be in the numerator. Whatever comes after the word to is going to be in the denominator. Gummies comes first, that's 460 in the numerator. Chocolates comes second, that's 320 in the denominator. You simplify that fraction and you get 23 to 16. What's the simplified ratio of chocolates to gummies? We just found gummies to chocolates. So chocolates to gummies, flip it around, 16 to 23. What's the simplified ratio of chocolates to the total amount? Now, this is easier than it looks. If there were 16 chocolates, then there would need to be 23 gummies. If there were 16 chocolates and there were 23 gummies, there would be 39 total candies. So if we say that there are 16 chocolates, there would be 39 total, and the ratio of chocolates to the total is 16 to 39. This is already simplified. We can't divide by any common factors. Let's take a look at number 3 here. 72x to the 4th y over 88x squared y to the 5th. We can divide 72 and 88 by 2. We divide them both by 2, and I get 36 over 44. I could divide 36 and 44 by 2. I do that. 36 divided by 2, I get 18. 44 divided by 2, I get 22. I could divide 18 by 2, and I get 9. I can divide 22 by 2, and I get 11. So we divide 18 and 22 by 2, and I'm left with 9 over 11. Now, there's a shortcut for the variables that we talked about yesterday. Find the larger exponent, which is in the numerator here for the x's. X to the fourth over x squared. The larger exponent is in the numerator. So x is going to be in the numerator. And we subtract the exponents. 4 minus 2, we get 2. So x squared is in the numerator. Y to the power of 1 in the numerator. Y to the power of 5 in the denominator. Look for that larger exponent, which is in the denominator here. Y is going to be in our denominator. And we subtract the exponents, 5 minus 1, and we get y to the power of 4. So 9x squared over 11y to the fourth. Here's supporting work for y, x to the power of 2 is in the numerator. Here's the supporting work for y, y to the power of 4 is in the denominator. You're not required to show this. Using the shortcut is absolutely acceptable. Simplify the monomial below. 39, x to the power of 7, y to the power of 4 over 13, x to the 7th, y to the 4th. 39 and 13, we can divide these both by 13. 39 divided by 13, and we get 3. 13 divided by 13, and we get 1. X to the power of 7 divided by x to the power of 7. All right, anything divided by itself is 1. Here's proof of that. We got 7x's up top, all being multiplied here. 7x's in the denominator, all being multiplied. They're all going to cancel out, which leaves us with 1. Anything divided by itself is 1. X to the power of 7 divided by itself is 1. If you recall also, though, x to the power of 0 is also 1. Anything to the power of 0 is 1. So however you want to think about this problem, you end up with x to the power of 7 divided by x to the power of 7 is 1. Same thing with the y's. Y to the power of 4 divided by y to the power of 4, that is also 1. So 3 times 1 is 3, divided by 1 is also 3. So we end up with an answer of just 3 on number 4. This is kind of a fun problem. If you want to pause the video and try to work it out on your own, you can, but Janet works every other day, Lynette every third day, and Mark every fifth day. All three work together on Tuesday, August 1st. Don't worry about the Tuesday part here, but August 1st, the first day of the month, they all work together. So on the first day of the month, Janet worked, Lynette worked, and Mark worked. We're going to go across here. We're going to go up to 10, 3, 4, 5, 6, 7, 8, 9, and 10. And then we'll do the same thing down here for 11 through 20, 11, 12. I'm going to pause the video. You can do the same thing. So I've got 11 through 20 there. I'm going to do the same thing for 21 through 30. There we go. So I got my calendar written out here. So Janet, Lynette, and Mark, they all work together on the 1st. So let's mark out every day that Janet works. She's going to be a J. She works every other day. First day, the third day, Janet. Fifth day, 7th. You get the idea all the way. It's every odd day for Janet is what it ends up being. It's every other day. So here we have all the days that Janet worked. Okay, now Lynette worked every third day. So let's do that. I'll do this in red. So here we go. 1, 2, 3. She worked on the 4th. 1, 2, 3. She worked on the 7th. 1, 2, 3. She worked on the 10th. 1, 2, 3. She worked on the 13th. 1, 2, 3. She worked on the 16th. 1, 2, 3. She worked on the 19th. 1, 2, 3. She worked on the 22nd. 1, 2, 3. She worked on the 25th. 1, 2, 3. She worked on the 28th. 1, 2, 3. She worked on the 31st. 31st. Let's do the same thing with Mark every 5th day. So here we go. 1, 2, 3, 4, 5. You worked on the 6th. 1, 2, 3, 4, 5. You worked on the 11th. 1, 2, 3, 4, 5. You worked on the 16th. 1, 2, 3, 4, 5. You worked on the 21st. 1, 2, 3, 4, 5. You worked on the 26th. 1, 2, 3, 4, 5. He worked on the 31st. I missed when I went through with Jenna. I did not do, she worked on the 31st, but she did. She worked on the 1st, the 3rd, the 5th, every odd day, right? 29th. Didn't work the 30th, but she did work on the 31st. So there you go. Put Janet in there at the 31st as well. How often will Janet and Mark work together? All right, well, Janet works every 2 days. Janet works every 2 days, and Mark works every 5th day. Mark works every 5th day. So you could count it up, and let's go ahead and do it really quick. They work on the 1st, and then Janet and Mark work together again on the 11th. And then Janet and Mark work together again on the 21st, and they work together again on the 31st. So they're working together every 10 days. But what if I told you there's a way to do this mathematically? If Janet works every 2 days or every other day, Mark works every 5th day, we can multiply 2 times 5 and we get 10. So they work together every 10 days. All right, nice that we can do that mathematically instead of just counting on the calendar here. Let's take a look at this one. On what date will Janet and Mark work together? It should be dates, not date, but they work together. We can look up front here, up top here, on the 1st, on the 11th, on the 21st, and on the 31st. So on the 1st, on the 11th, on the 21st, and on the 31st. There you go. On what day will all three work together again? Now, from our calendar up top, we know that they don't work together, all three of them, until the 31st. But let's see how we can do this mathematically. Janet works every other day or every 2 days. Mark works every 5th day. Lynette works every 3rd day. So mathematically, 2 times 5, that's 10, times 3, that's 30. 30. They work together every 30 days. And if they work together on the 1st, you add to that 30 days, and they'll work together again on the 31st. There's some mathematical proof of them working together every 30 days. It's a lot easier to use multiplication as opposed to writing out this chart here. It's good to see that the chart provides proof of the mathematics, but multiplying definitely is going to save you some time. A blank, that'd be a multiple of a number is a product of that number and any whole number. So the multiples of 2, 2, 4, 6, 8, you know these, 10, 12, 14, I'm going to go up to 20, 16, 18, and 20. Let's do the multiples of 5, 5, 10, 15, 20, 25. I'm going to go up to 30, 30. There you go. Multiples that are shared by 2 or more numbers are called common multiples. So as I look up top there, do we see any common multiples? I see a common multiple here at 10 and 10. I see a common multiple at 20 and 20. Now these go on forever and these go on forever. So what's the next common multiple after 20? It's going to be 30. I didn't show it up in the top row there, but 30 and 30, they are common multiples, even though I didn't show it. There you go. 10, 20, 30, then 40 is going to be next. You get the idea. What's 2 times 5, by the way? 10. So every 10 numbers will be common multiples between 2 and 5. So we'll say the least of the non-zero common multiples of 2 or more numbers. Well, what's the least common multiple up top here? It's 10 and 10, right? So 10 is the least common multiple. The least of the non-zero common multiples of 2 or more numbers is called the least common multiple, or LCM for short. There you go. When two numbers like 2 and 5 don't have any common factors, all you have to do is multiply them together. That would not work for 10 and 10 and 5. 10 and 5 have common factors, right? 5 is a common factor of 10 and 5. So like 10 times 5, that's 50. That's not the LCM. It is a common factor of 10 and 5, but it's not the LCM. What's the LCM of 10 and 5? It's 20. So when you have numbers like 10 and 5, they're easy to think about their multiples, or maybe you want to write them out. Then just thinking about the multiples is a good way to go. We have methods for finding the LCM, like we're going to use right here in method 1, prime factorization. Let's do the prime factorization of 30 and 36. 30 is 2 and 15. 15 is 3 and 5. 36 is 2 and 18. 18 is 2 and 9, and then 9 is 3 and 3. So let's write out the prime factorization of each. This is 30 is equal to 2 times 3 times 5. 36 is equal to 2 times 2 times 3 times 3. Now this looks like GCF so far, but it's about to take a turn here in just a second, and it's gonna be different. So here's what we do. We start out by the common, looking for common factors. 2 and 2, we'll write that down. Do we see any more? 3 and 3, we'll write that down. Now at this point, the GCF would be 6. But we're not worried about the GCF. We're trying to find the LCM, the least common multiple. So to find the LCM, we're going to write down all the leftovers. I've got a 5 left over. I'm going to write that down. I got a 3 left over. I'm going to write that down. And I got a 2 left over. I'm going to write that down as well. Now we multiply. 2 times 3 is 6. 6 times 5, that's 30. 30 times 3 is 90. 90 times 2 is 180. So 180 is our least common multiple between 30 and 36. Oh. Method number 2 is we can list out the multiples. So 18, what are the multiples of 18? Well, 18, 36. You don't have to use a comma if you don't want to. After 36 would come, what would that be? 54. After 54 would be 72. Let me pause there for a second. For 12, the multiples are going to be 12, 24, no matches so far. 36, oh, look at there. 36 is my LCM of these two. So the LCM is 36. When would we use this method? We would use this method when the numbers are relatively small and they you can go through the multiples pretty easily. If you have large numbers, you probably don't want to use this method. So if we had like, instead of 18, if we had like 182 or 180, and instead of 12, if we had like 120, maybe you would not want to use this method. But those are probably bad choices because you could probably think about those multiples even. But if it were like 124 and 188, you'd probably want to use method 1 where you did the prime factorization and then multiplied the common factors and then the leftover factors as well. So try the next 3 examples on your own. Pause the video now, try those 3 examples, give it a shot. All right, 24 and 15, whichever method you used, I did prime factorization here. So 24 is 2 and 12, 12 is 2 and 6, 6 is 2 and 3. So the prime factorization of 24 is 2 times 2 times 2 times 3. 15 is 3 times 5. So 3 times 5, there's prime factorization of 15. Common factors, 3 and 3, write that down. 5, write that down. And then 2, 2, 2, write that down. So we get an LCM of 120. LCM of 120 there without problem. Example 3. This next one should say example 4. It's a typo there. Find the LCM of 40 and 54. If you haven't done this one yet, you need to pause the video and do it now. 40 and 54. 40 is 2 and 20. 20 is 2 and 10. 10 is 2 and 5. So the prime factorization of 40 is 2 times 2 times 2 times 5. Same thing for 54. 2 and 27. 27 is 3 and 9. And then 9 is 3 and 3. So 54 is 2 times 3 times 3 times 3. We look for common factors. We got 2 and 2. Write that down once. We have no other common factors, so everything else gets written down. 5 3, 3, 3, 2, 2. If you're multiplying numbers like this, I'd recommend you start with the larger ones first. 5 times 3 is 15. 15 times 3 is 45. 45 times 3, that is 135. 135 times 2 is 270. 270 times 2, 540. And then 540 times 2 is 1080. There you go. And the last one, example 5. If you haven't done that one yet, pause the video now and give that one a shot. All right, looking now at example 5. Oh, we have variables at play here. No big deal. You can handle it. It's the same method. Find the LCM of 12a squared b and 8ac. All right, so 12, this is 2 and 6. 6 is 2 and 3. 8 is 2 and 4. 4 is 2 and 2. You could probably also just think about the multiples of 12 and 8, and you would get 24. But for the sake of the variables here, I'm going to show the prime factorization. So 12a squared b. Make sure you show this on the left side. On the final exam, we had some folks that were not showing this on the left side. It's important that you do. So this is 2 times 2 times 3. 2 times 2 times 3. A squared is a times a. B is just b. 8 is 2 times 2 times 2. AC is just AC. So we look for common factors. We get a common factor of 2 and 2. Write that down. 2 and 2. Write that down. We have no other common factors with the numerical values, so write down the leftovers here, 3 and 2. We do have a common factor in the A's, A and A, cross those out, write it down once. And then the leftovers have no other matches, so A gets written down, B gets written down, C gets written down. Then we just multiply it all together. 2 times 2 is 4, 4 times 3 is 12, 12 times 2, we get 24. A times A is A squared, B is just B, C is just C. So there you go. Susie sneezing. Susie sneezes every 5 minutes, and Alexandra coughs every 4 minutes. Susie sneezes, and Alexandra coughs at the start of class. In a 40-minute class period, how many times will Susie sneeze and Alexandra cough simultaneously? See if you can do this one. So let's think about the LCM of 5 and 4. 5 times 4, it's 20. So in a 40-minute class, at the bell, that is time 0. Time equals 0. So when the bell rings, that's not 1 minute into class, that's 0 minutes into class. So they sneeze and cough together at the 0-minute mark. They'll cough and sneeze together again at the 20-minute mark, and then they'll cough and sneeze again right as the bell rings at the end at the 40-minute mark. So how many times will Susie sneeze and Alexandra cough simultaneously during the class? 3 times. We'll say Susie and Alexandra will cough and sneeze simultaneously. Three times. In a 40-minute class, or in the 40-minute class. How about that? At the zero-minute mark, at 0 minutes, we'll just do 0 minutes, 20 minutes, and 40 minutes. There you go. All right, guys, thanks for watching. Hope you have a great day. Please complete that 3rd document in class right now. Whatever you don't finish, let's see here. Let's do the evens for in class and do the evens for homework as well. So if you don't finish the evens, do them for homework. Thanks, guys. Have a great day.